So we're talking about gravity, or gravitation, okay, and we know that it's one of the 4 fundamental forces. We know that it is always attractive, no negative gravity, okay, and we know that it is the force between masses. The third thing, force between masses. Okay, remember electromagnetic force, force between charges, electricity. This is force between masses, gravity, okay? And we have a model, and the model we use, still going strong, is Newton's law of gravitation, the model from Newton, okay? And Newton's law of gravitation said that F was proportional to the product of the masses, two masses, and inversely proportional to the distance between them. Okay? Right? Now, this model indicates that the force acts instantly, which kind of goes against our idea of speed of light being a maximum speed. It's a model. The model explains what goes on very well. It worked perfectly. This model worked well enough to get people onto the moon and back. Okay, but the model actually doesn't work, isn't good enough for GPS, the GPS systems that we use to locate ourselves with our watches and so on. And there's an improved model from Einstein. Einstein's general theory of relativity has the improved model. Not relevant to us, but just to be aware, we're using models. Remember, we keep saying about physics, it's making models and using the simplest model works. This model works almost all of the time. Now, we know that the force between masses is very small normally, because otherwise we would all be stuck to each other. Okay, so how come? Okay, so if you look at this, to make this small, the constant has to be a really small number. Okay, otherwise, if the masses were reasonably large and the distance reasonably small, the force would be large. This has to be a tiny number, and it is. And it's called Newton's it's the universal gravitational constant. Okay, uppercase G. It looks okay like that, but when you write it like that, you suddenly realize this is a really, really small number. And that's what we need. We have a really small number, to make sure that we have a really small number so that when we get the force, we're going to get a really small force unless one of the masses is really large. That's why gravitational force is negligible when it comes to subatomic particles, which are very small mass, and it's even not really that important between masses on Earth. Okay, if that G was large, we would all be stuck to each other. There'd be force of attraction between us all of the time. We would be absolutely in trouble at the moment with COVID, because there's no way we'd be able to maintain a 2 meter distance. But this number, the fact that it's small, makes life a lot easier for us. Okay, so that's where we're at. All right, that's the first bit. Second thing we're interested in is the speed, okay, that a satellite orbits the Earth. The speed that it orbits the Earth. Okay, and we have a formula for that, and we look at the proof of it in the Kepler's proof that we have to know. Now, what's important here is that formula is not in the tables, and you need to know it. Okay, v squared is gm over r. Now look at it. Okay, the smaller the radius, v squared is proportional to r, inversely proportional to r. So the smaller the radius, the greater the velocity. So the closer you come, the greater the velocity. You'll see that in one of the clips in a minute. Okay, and watch the clips. Okay, do watch the clips, because they kind of reinforce what we're doing here. Right. The time for one revolution is our third formula. Okay, and we'll drive this in a minute. Okay, so the way we've written there, m there is the mass of the central body. Okay, so t squared is 4 pi squared r cubed over gm, the mass of the central body. That's the third formula. Okay, we also have, remember, periodic time is the length of the orbit divided by the velocity. Again, formula here that isn't in the tables directly, but you really need to know. Okay, you really need to know. What supplies the orbits? Okay, what supplies the centripetal force to keep it going in a circle? Okay, sorry, and that's the gravitational force. So the centripetal force is the gravitational force, and calculations that we look at tomorrow in gravitation, calculations in gravitation involve circular motion as well. So what you need to be able to do is understand your circular motion, understand these formula, okay, and then we combine them and it goes from there. Okay, so the plan is that tomorrow I will do tomorrow will involve calculations, and we will see how they go with gravitation. So you'll have calculations tomorrow, and you will then, having done the calculations, you will have an assignment for the weekend on questions on gravitation, which are inherently part of circular motion. So you will have your circular motion calculations done as well before that. Okay.